Dear students, today we will discuss 15 questions from magnetism, almost a theory-oriented topics compared to the previous chapters. Okay, let's start from the first question onwards. First question is about the field and potential due to a bar magnet. A bar magnet is almost equivalent to an electric dipole. North pole is equivalent to positive charge and south pole is equivalent to negative charge or minus Q. Now, about the equatorial and axial points. If a bar magnet is kept at a position and if you observe the field at an axial point, that is, at a point on the axis of the bar magnet, the flux density due to a short bar magnet, the field or flux density at an axial point is mu by 4 pi p by r cube for an equatorial point and mu by 4 pi 2p by r cube at an axial point. And if the bar magnet is not short, that is, if its length is considerable compared to the distance of the point, the flux density at an axial point is B equal to mu by 4 pi 2pr by r square minus l square whole square. And the flux density at an equatorial point is mu by 4 pi p by r square plus l square whole raised to 3 by 2. Now, the question is, pick out the correct choice. First choice is field along the equatorial axis is 0. Let's discuss. Bar magnet, then south pole, north pole, field line starts from the north and passes through the south. Means the magnetic field line is directed from the north pole to the south pole externally and south to north internally. Here, equatorial axis means an axis perpendicular to the bar magnet through its center. At an equatorial point, the field line is exactly anti-parallel to the direction of the magnet, that is perpendicular to the equatorial axis. That is, the field along the equatorial axis is 0. That is, at an equatorial point, the magnetic field is perpendicular to the equatorial axis or parallel to the direction of the bar magnet but in the opposite direction of the magnetic moment. Therefore, the field at an equatorial point, along the equatorial point, field along the equatorial point is actually 0. Therefore, first choice is field along the equatorial axis is 0. That is a correct choice. Then second choice, potential at an equatorial point is 0. That's also correct. Potential at any point on the equatorial point will be 0. Now the third choice is field along the axis of a bar magnet is always 0. Field along the axis of a bar magnet means axis of the magnet comes like this. Field is not 0 at an axial point. Field along the axis of a bar magnet is always 0. That's a wrong statement. Then the correct statement, the correct choices, correct answer is D. That is, A and B are correct. For the first question, the correct choice is D. D choice is the correct answer. Question number 2. Pick out the correct choice. Again, another theoretical question. And this is about ferromagnet, paramagnet and diamagnet. First, I will explain what are these materials. What's the nature of these three types of material. Based on the magnetic behavior, materials can be divided into 3. Paramagnetic, diamagnetic and ferromagnetic. Materials are divided into 3: dia, para and ferro. First, I'll tell you something about diamagnetic. Substances which are feebly repelled away from a region of magnetization are diamagnetic in behavior. And for paramagnet, feebly attracted towards a field. But ferromagnet, in the case of ferromagnet, it will be strongly attracted towards the field region. Substances which are feebly repelled away from a region of magnetization are diamagnetic. Feebly attracted towards a region of magnetization are paramagnetic. And those which are strongly attracted towards the region of magnetization are ferromagnetic. These are the difference in the basic property. Then, if a paramagnet is kept in a uniform magnetic field region, it will align parallel to the field direction. Paramagnet is kept in a uniform field region, it will align parallel to the field region, field lines. But if a diamagnetic material is kept in a uniform field region, it will be aligned perpendicular to the field direction. That is, the material sets itself with its longer axis perpendicular to the field direction. Magnetization is low, independent of temperature, and is lost when the applied field is withdrawn. That is, it can act as a temporary magnet only, or only in the presence of an external field it can act as a diamagnetic, or it can act as a magnet. Then, if a paramagnet is heated, its magnetization will be reduced. Once again, I'll repeat. If a diamagnetic material is kept in a uniform field, it aligns parallel to the field direction. Then magnetization is low, independent of temperature, and is lost when the applied field is withdrawn. Then magnetic susceptibility is negative for a diamagnetic material. Mu is less than mu 0. Mu means permeability of the medium. Mu is less than mu 0 and mu r is less than 1. Now, we'll discuss the case of paramagnet. Substances which are feebly attracted towards a region of magnetic field are paramagnetic. In a uniform field, a paramagnetic material aligns parallel to the field direction. Magnetization is low, decreases as the temperature increases, and is lost when the applied field is withdrawn. Susceptibility is positive. Mu is greater than mu 0 and mu r is greater than 1. These are the properties of paramagnet. Then ferromagnetic. Substances which are strongly attracted towards a region of magnetization, or which can be very easily magnetized, or which can act as a permanent magnet even in the absence of an external field, are ferromagnetic in behavior. In a uniform field, it aligns parallel to the field direction. Then, what about the heating process? Magnetization is very high, decreases as the temperature increases, and exhibits the phenomenon of hysteresis. The phenomenon of hysteresis is applicable or satisfied only for ferromagnetic material. And best examples for ferromagnetic materials are iron, cobalt, and nickel. Now we'll go through the choices one by one. The first choice is, for a ferromagnet, remnants is 0. I'll explain what is remnants and what is quasi-field. If an external magnetizing field is given to a ferromagnetic material, after some time, it will have some magnetization. The received field strength within the material is called magnetization, and the externally applied field so as to magnetize the given material is called magnetizing field. We are going to plot these two. The externally applied field along the x-axis and the field strength received by the material, magnetization, along the y-axis. Initially, if the given field is gradually increased, the magnetization will also increase and almost a saturation state is obtained. Then, if the applied field is withdrawn, the magnetization also decreases but does not coincide. It follows a different path. O, A, B. This remaining magnetization even after the withdrawal of the applied field, that's called remnants. Here OB, remnants. OB is called remnants. Then, in order to demagnetize the material, we have to apply a negative magnetizing field like this. If a negative field is given, the graph comes like this. Once again, if it is reversed, again a saturation. Then, if it is again reversed, finally we get a closed loop. This closed loop is called hysteresis loop. The remaining magnetization even after the withdrawal of the applied field, here OB, is called remnants, and that property of retaining the magnetization is called retentivity. Then the negative field required to demagnetize the material is called coercive field, and that property is called coercivity. Here OC gives the coercive field. Coercive field. Now, let's go to the question. The first choice is, for a ferromagnet, remnants is 0. For a ferromagnet, there is a non-zero remnants OB. Some magnetization is remaining even after the withdrawal. Remnants is 0, that statement is wrong. Then, second choice, for a ferromagnet, coercive field is 0. Here, coercive field is also non-zero. That's also wrong. Remnants and coercive field are non-zero for a paramagnet. For a paramagnet, immediately after the withdrawal of the given field, the entire magnetization will be ejected out. Nothing will be remaining there. That's also not correct. Then, last choice, D. Remnants and coercive field are non-zero for a ferromagnet. That's the correct choice. That is, here for the second question, the correct answer is remnants and coercive field are non-zero for a ferromagnet. That is, D choice is the correct answer. All the other three are not correct. Answer is D. Now, the question number 3. Third question is about the unit. To understand the unit, first I will go through each and every terms of magnetism. First, the most elementary or the basic term in magnetism is pole strength, which is equivalent to a charge in electrostatic. Pole strength I'll take the symbol M, and its unit is ampere meter. A for ampere, M for meter. Pole strength. Pole strength has a unit ampere meter. That's the most elementary quantity of magnetism. Now about the magnetic moment. The product of one of the pole strengths of a magnet and the distance between the two poles, that is normally the length of the bar magnet, is called magnetic moment. Always the length of a bar magnet will be represented as 2L. L means half length of the magnet, south pole, north pole. Product of one of the pole strengths and the distance between the two poles, 2L, this product is called magnetic moment. For pole strength, the SI unit is ampere meter. Therefore, for magnetic moment, ampere meter into length, that is ampere meter square. This is the SI unit of magnetic moment. Now, the magnetic moment per unit volume, that is 2Lm divided by, instead of volume, length of the bar magnet and the cross-sectional area, 2L cancels. Then pole strength divided by area. This is called intensity of magnetization, and it will have the unit ampere meter divided by meter square, ampere per meter. Now, about the field lines of bar magnet. The path followed by an isolated unit north pole around a bar magnet, in a region around a bar magnet. That's the definition of a line of force. Path followed by an isolated unit north pole. A line of force originating from the north pole and passes through south pole, that is a field line of a magnet, is directed from north pole to the south pole externally and south pole to north pole internally. The tangent drawn to the line of force gives the direction of the magnetic field at that position. Two lines never intersect, and the collection of lines of force is called magnetic flux. Collection of lines of force, magnetic flux. I am representing it by phi. Then flux per unit area. Collection of magnetic field lines, that's called magnetic flux. Flux per unit area is called flux density or magnetic induction. Now, the ratio of the flux density to the field in ampere per meter or intensity of magnetization gives the magnetic permeability of the medium. These are all the terms, fundamental terms of magnetism. First, pole strength, its SI unit is ampere meter. Then magnetic moment 2Lm equal to P. Its SI unit is ampere meter square. Then intensity of magnetization represented by capital H, ampere per meter. Then flux. Flux has SI unit Weber and it has a smaller unit Maxwell. The SI unit of flux is Weber, WB or Weber. Another unit of magnetic flux is Maxwell. Two units of magnetic flux are Maxwell and Weber. Weber is the SI unit. Here the question is about the unit of some quantities. Question number 3. In question number 3, the SI unit of magnetic moment. First one, ampere meter. It is the unit of pole strength. Second one, ampere meter square. It is the unit of magnetic moment. Here, that's the correct answer. Third one, Easted, OER-STED. It represents the strength of a magnetic field. Then Tesla. Tesla is the unit of magnetic flux density or magnetic induction. Therefore, here the correct answer is B choice, ampere meter square. Ampere meter square is the SI unit of magnetic moment. B choice is the correct answer. Question number 4. A bar magnet bends such that it covers 3/4 of a circular loop. The moment becomes dash. Okay, after bending, what happens to the moment? Bar magnet bends such that it covers 3/4 of a circular loop. Like covering 3 quadrants. If the magnet is in the straight form, it will have a length 3/4 of 2 pi r, 3/4 of circumference. 3/4 of 2 pi r into pole strength will give the magnetic moment before bending. Now, after bending, the distance between shortest distance between the two poles is only √2r. R, then the separation between the poles √2r. Therefore, the magnetic moment after bending is √2r into pole strength. In first case, 3/4 of 2 pi r into pole strength. In the second case, √2r into pole strength. Now the question is, after bending, the moment becomes dash. How many times the initial? Therefore, we have to divide the second equation by the first one. Equation 2 divided by equation 1. √2r divided by 3/4 of 2 pi r. Then 2√2 by 3 pi. Therefore, the answer is P2 final moment is 2 root 2 by 3 pi times the initial moment. 2 root 2 by 3 pi times the initial moment. Therefore, the correct choice is C. Once again, I'll repeat. The first question is 2 by pi. First choice is 2 by pi times the initial moment. That's wrong. Second choice is 2 root 2 by pi times the initial moment. That's also wrong. Third choice is 2 root 2 by 3 pi times the initial moment. That's the correct answer. The correct answer is C. Question number 5. A bar magnet bends at right angle. Bends at right angle with the arm ratio 2:1. Okay, listen here. Initially, straight line. In the second case, bar magnet bends at right angle, arm ratio 2:1. 2L, L. Then initially 3L. Now, the separation between the two in the second. First case, the moment is P1 equal to 3L into pole strength. Second case, 2L, L. Then root 5L is the separation between the two poles after bending. P2 is root 5L into pole strength. Now, how many times the initial? P2 by P1. That is second by first gives root 5 by 3. Therefore, the answer is root 5 by 3 times the initial moment. C choice, root 5 by 3 times the initial moment, or P2 equal to root 5 by 3 into P1. That's the meaning of C choice. Question number 6. This is about the time period of oscillation of a bar magnet. If a bar magnet is suspended freely, and if an external magnetizing field is brought near for a moment, the magnet undergoes an oscillation with a definite time period. And the time period of oscillation of an oscillating magnet depends on the shape and size of the magnet, or mathematically the moment of inertia of the magnet, magnetic moment, and the externally applied field. And the correct equation is given by, that is the equation for the time period of oscillation of a suspended magnet, is given by T equals 2 pi root of I by P dot B, where I is the moment of inertia of the magnet. For a bar magnet, this I can be approximated as ml square by 12. I for a bar magnet can be approximated as ml square by 12. Here m is the mass of the bar magnet, P is the magnetic moment, and B is the externally applied field or flux density of the externally applied field. Now, in the given question, the bar magnet divides into 3 identical parts parallel to its length. Then, the time period of oscillation of each, let us check one by one. Moment of inertia is approximated as ml square by 12. Bar magnet divided into 3 means mass becomes 1/3. L remains unchanged. Therefore, the moment of inertia becomes I by 3. Mass is now 1/3 only. Now, P, 2Lm. 2L into pole strength gives the magnetic moment. If the width of a pole is reduced, the pole strength will be reduced. Actually, by Weber's molecular magnetic theory or domain theory, the strength of a pole is because of the presence of certain simpler units called molecular magnets. And the strength of a pole is always decided by the number of molecular magnets acting at the pole. If the width of a pole is reduced, the number of molecular magnets acting at that pole will be reduced, and hence the pole strength will be reduced. Therefore, here, if it is divided into 3, the pole strength becomes 1/3 of the initial, but length remains unchanged. Therefore, the magnetic moment becomes 12 into pole strength. Pole strength is reduced to 1/3. Length remains unchanged. Therefore, moment becomes P by 3. And B is the externally applied field. It has no change by dividing the suspended magnet. Therefore, here the moment of inertia becomes 1/3, magnetic moment becomes 1/3, and the externally applied field remains unchanged. Therefore, the time period of oscillation 2 pi root of I by P dot B becomes unchanged. So that is, I is 1/3, I is now only 1/3 of the initial, P is now only 1/3 of the initial. Therefore, time period has no change. Or the time period remains exactly the same, T1 equal to T2. Therefore, here the answer is almost remains the same. Here, choices given as almost remains the same and remains exactly the same. Therefore, you should be very careful. Here, we approximated the moment of inertia as ml square by 12. For a rectangular lamina, the actual moment of inertia is m into L square plus B square by 12. But for a bar magnet, breadth is negligible compared to the length, and hence it is approximated as ml square by 12. That's why almost remains the same. In the given choice, it is written as almost remains the same. Therefore, the correct choice is C, almost remains the same. C choice is the correct answer. Next one is also a theory question. Pick out the correct choice. For a short bar magnet, axial and equatorial field. Question is about the axial and equatorial field. For a short bar magnet, as earlier mentioned, the axial field is mu by 4 pi 2p by r cube. And for at an equatorial point for a short magnet, flux density is mu by 4 pi p by r cube. That is, for a short magnet, actually, the axial field has a magnitude twice that of the equatorial field. One p by r cube, other one 2p by r cube. Axial field is mu by 4 pi 2p by r cube, which has twice the magnitude as that of the equatorial field. Now let's select the choice one by one. The first choice, A choice is the axial field will be greater compared to the equatorial field. Compared to the equatorial field, axial field is greater. കൃത്യമായി പറഞ്ഞാൽ equatorial ഫീൽഡിൻ്റെ twice ആയിരിക്കും axial field for short magnets. Now about the second choice. The field at an end-on position will be smaller compared to the broadside-on position. End-on position means axial point. Broadside-on position, in the case of broadside-on position, it is an equatorial point. These are different terms of axial and equatorial. The field at the end-on position, that is field at an axial point, will be smaller compared to that of broadside-on position. It is wrong. Broadside-on position is equatorial point. That will be smaller actually. Then third choice, field at the broadside-on position, that is at an equatorial point, will be half the field at the end-on position for the same distance. That is a correct choice. For the magnitude of the equatorial field will be half of the magnitude of the axial field. Once again, we'll go through the choices. The axial field will be greater compared to the equatorial field. That's correct. Field at the end-on position will be smaller. That is wrong, because field at the end-on position at an axial point will be greater. Then C choice, field at the broadside-on position will be half of the field at the end-on position. That is the correct choice. At an axial field for the same distance, field will be twice that of equatorial point. Therefore, here A and C are correct. Two choices are correct. A choice is correct, C choice is correct. Therefore, the correct answer is A and C are correct. That's D is the correct choice. Question number 8. Let us discuss something about the terrestrial magnetism. Means something related to Earth. Earth has an axis of rotation and the geographic North Pole and geographic South Pole is based on this axis of rotation. But in addition to the geographic axis, Earth has one more axis, magnetic axis, equivalent to a bar magnet passing through the center of gravity of Earth. The North Pole of that imaginary magnetic axis comes closer to the geographic South. And if a bar magnet is freely suspended, it will be aligning along the north-south direction. An imaginary vertical plane passing through the North Pole and South Pole of a freely suspended magnet is called magnetic meridian. The angle between the magnetic meridian and the geographic meridian at a place is called declination. Then, the angle between the total field intensity at a place and the direction of the horizontal component is called dip or inclination. Dip, declination, and horizontal component of Earth's magnetic field. These three are collectively called magnetic elements of Earth. And some important points are also there in magnetic maps. A line connecting points of same declination is called isogonic line. Then points of zero declination is called line connecting points of zero declination is called agonic line. Then line connecting points of same dip is called isoclinic line. And line connecting zero dip, points of zero dip is called actinic line or magnetic equator. And line connecting points of equal horizontal component of Earth's field is called isodynamic line. These are very important points to remember. And we have to study those names by heart. Now let's go through the choices one after the other. The first choice. Question is, in magnetic maps, line connecting points of zero dip. The answer is magnetic equator or actinic line. C choice is the correct answer. Magnetic equator or actinic line. That's the correct choice. C is the correct choice. Question number 9. Here, some important point about dip. Dip is the angle between the total field intensity at a place and the direction of horizontal component. Therefore, dip at the pole is 90 and the dip at the equator is 0. At the pole, the field is purely vertical. Therefore, horizontal direction and the total field intensity will be 90. Dip at the pole is 90. Dip at the equator is 0. Now, here the question is, dip at the equator is, then the correct answer is 0. Very simple theory question to remember. Answer is B. Question number 10. That's about the field intensity. For a short bar magnet, the magnetic field at an axial point at a distance of 10 centimeter, the magnet at a distance of 10 centimeter from the center of the magnet is 20 units. Then for the same distance, what's the equatorial field for the same distance? Okay, we have already mentioned for a short bar magnet, the axial field is mu by 4 pi 2p by r cube. And at an equatorial point, B equal to mu by 4 pi p by r cube. That is, for the same distance, equatorial field has a magnitude equal to half of the axial field. Here the axial field is given as 20 units. Therefore, the equatorial field is only 10 units. Therefore, the correct answer is 10 units. That is A choice is the correct answer. Question number 11. It's also about a unit. The SI unit of magnetic flux. Magnetic flux has two units, Weber and Maxwell. SI unit is Weber. Then, let's discuss something about the other choices. Maxwell, it's the unit of flux. Then A and B both are about flux. Tesla, flux density or magnetic induction. Here the question is SI unit of magnetic flux, that is Weber. That is A choice is the correct answer. Weber, Weber. That's the SI unit of magnetic flux. Again, some theory questions about dia, para and ferromagnetic material. Pick out the correct choice. That's the question. Susceptibility is negative for diamagnet. For a diamagnet, it will be feebly repelled away from a region of magnetization and susceptibility is negative. Then B choice, susceptibility is negative for a paramagnet. No, for paramagnet and for ferromagnet, susceptibility is positive. Then third choice, susceptibility is positive for a paramagnet and ferromagnet. That's a correct choice. Then D, A and C are correct. Here, the answer is D actually. That is, susceptibility is negative for a diamagnet. That's a correct choice. Then C choice, susceptibility is positive for para and ferromagnet. That is also correct. Therefore, the correct answer is A and C are correct. That's D choice is the correct answer. About question number 13. Very direct question. An example for ferromagnet. While discussing the properties of ferromagnet, I mentioned the three examples, iron, cobalt and nickel. Here the given example is iron. Therefore, the correct choice is C. Example for ferromagnet is iron. Question number 14 is about Curie law. What is Curie law? For a paramagnet, I will something about para and ferro. A ferromagnetic material means which can be very easily magnetized, which can act as a permanent magnet even in the absence of an external field, and which is strongly attracted towards a region of magnetization. But if a ferromagnetic material is heated above a particular limiting temperature or cutoff temperature called Curie temperature, it loses its ferromagnetism and becomes paramagnetic in behavior. That is, above Curie point or Curie temperature, a ferromagnetic material becomes paramagnetic in behavior. Then, for a paramagnetic material, Curie law is applicable. What is Curie law? The susceptibility of a paramagnetic material is inversely proportional to the absolute temperature. That is, for a paramagnetic material, the susceptibility psi is inversely proportional to the absolute temperature. Psi equal to C by T, where C is called Curie constant. Then, what is Curie law? It is applicable to which material? Then, applicable only to paramagnetic material. And Curie law is for a paramagnetic material, the susceptibility is inversely proportional to the absolute temperature. Then about the Curie temperature, if a ferromagnetic material is heated above a particular value called Curie temperature, it loses its ferromagnetism and becomes paramagnetic. That critical temperature cutoff point, that is called Curie temperature. Now we'll go through the choices. First choice is Curie law is applicable to ferromagnet only. No, it is applicable to paramagnet only. Then second choice, Curie law is applicable only to paramagnet. That's a correct choice. Then third choice, Curie law is applicable to both ferro and para. No, wrong. It is wrong. Curie law is applicable only to dia. It is also wrong. Therefore, here the correct choice is B. Curie law is applicable only to paramagnetic material. B choice is the correct answer. Question number 15. Dimensional formula of magnetic permeability. First of all, the SI unit of magnetic permeability is Henry per meter. And Henry is the unit of inductance, self-inductance or magnetic inductance. Half Li square equal to energy. This is the equation for the energy stored in an inductor. Therefore, the dimensional formula of inductance, self-inductance or magnetic inductance can be easily identified by this expression as M L square T raised to minus 2, this is for work or energy, divided by I square, therefore I raised to minus 2. This is the dimensional formula of self-inductance, and it has a unit Henry. Henry per meter is the unit of permeability, means this dimensional formula divided by the dimension of length. Therefore, mu has a dimensional formula m L square T raised to minus 2 I raised to minus 2 divided by Henry per meter, means a length, that is m L T raised to minus 2 I raised to minus 2, m L T raised to minus 2 I raised to minus 2. A choice is the correct answer. That is, the dimensional formula of magnetic permeability is mL T raised to minus 2 I raised to minus 2, and it is derived from its unit Henry per meter. Henry is the unit of inductance. We identified the dimensions of inductance, then divided by length. Therefore, the answer is A choice. Now we have completed 15 questions from the topic of magnetism. Actually, it's a theory-oriented section. എന്നാലും ചോദിക്കാൻ ചാൻസ് ഉള്ള സിമ്പിൾ പ്രോബ്ലംസ് ഞാനതിൽ ഇൻക്ലൂഡ് ചെയ്തു. അങ്ങനെ some simple problems and some theory questions are covered almost. When you go through these 15 questions, you will get some idea about the simple problems and the theory portions of this magnetism. Thank you.